solve the number of equations for the number of unknowns that you have. So let's do a very simple example again that we did at the end of the last class. That we have a voltage source, and then we have another voltage source here. And then this is given to be minus 2 volts. Okay, and we have 1 ohm, 3 ohms, and 2 ohms here. And so the first thing to do is to assign loop currents. So we see 2 loops in this thing. We see 1 loop, and then we see another loop over here. And we call the current in loop 1 I1, and then the current in loop 2 I2. Okay? We imagine the current to be flowing in this loop in this manner. This is what the loop current means. And then we imagine the current I2 to be flowing in this loop in this manner. So you would imagine that I1 is flowing in this branch. I1 is also flowing in this branch. So it is also there, and then there will be I1 flowing in this branch. Okay? And then you would imagine that I2 is flowing in this branch. I2 is flowing here as well as here, and then I2 is flowing in this branch. And in this branch over here, you have the 2 loops flowing in the opposite direction. So the current that's flowing down is I2 minus, or I1 minus I2. Okay, I1 minus I2 is what it means. So you get all the currents on the branch. The next thing you do is to apply Kirchhoff voltage law. Okay, Kirchhoff voltage law is that this current in the textbook is also called Ix. Okay, just to be sure that if you go back and check what Ix is, Ix, as you say, is the current on the common branch is I1 minus I2. Okay, that's what Ix is. Then you apply Kirchhoff voltage law. So Kirchhoff voltage law can be applied 2 ways actually. One way is applied on a loop, and when the Kirchhoff voltage law is sum over a loop, it should sum up to 0. Okay. Another way to apply Kirchhoff voltage law is that if I have a whole bunch of resistance hooked up together, I need not apply this on the loop, but if this is A, this is B, and if the total voltage is VAB, okay, VAB is V1 plus V2 plus V3 plus V4. Okay, so another way of not applying Kirchhoff voltage law, not in the loop, is that this voltage drop is just the sum of the individual voltage drop on each segment. Okay, so sometimes we apply the Kirchhoff voltage law in this manner, not in the loop, but over individual segments. So, but in this example over here, we will apply Kirchhoff voltage law on loop 1. Okay, so we walk around in the loop, and then the total voltage drop should add up to 0. And we decide to give a sign convention. When we have a voltage rise, we give it a negative sign. So as you walk from here to here, we have a voltage rise, because the voltage here is higher than here. Okay, so it is minus 5. And then as we go on this one over here, then there is a voltage drop. Because the current is flowing in that direction, there will be higher potential here than the potential here. Okay, if the current is flowing there. So the voltage is something like that. There will be a voltage drop, and that voltage drop is equal to what? We give voltage drop a plus sign. What is the voltage drop across the 2 ohm resistor? 2 times I1, very good. Okay. And then we have another voltage drop across this 1 ohm resistor, and that is just 1 times I1 plus I2, minus I2. Okay, so that is the KVL for loop 1. KVL for loop 2, we do the same thing. We walk around this loop. Okay, this is a plus, this is a minus. This would be a plus, this would be minus as we walk around this loop. So the total voltage drop should also add up to 0. And the first time we walk, say we walk beginning from here to here. Okay, so that is a voltage rise. That is voltage rise. That is 1 ohm times I1 minus I2. Okay, that is the first branch of this loop. And then as we walk from here to here, that is a voltage drop. So we give it a plus sign. So it's 3I2. Okay? And as we walk from here to here, if we do not look at this at the beginning, is this a voltage drop or a voltage rise? Voltage drop. So we should give a positive sign to the value of this voltage drop. Okay, so it should be plus. But then this voltage is, if I open this up and show it to you, has a negative sign. And you should give this voltage drop a -2 sign. Okay, is that clear? Some of you might get confused as to whether I should have a plus or minus sign at the end. Okay? Then you have these two equations, two unknowns. You solve for I1 and I2. And bingo, you get the answer. Okay, is that clear? So some of you were very confused about the last step as to what I should do or what we should do. So are there any questions regarding this current loop method? Yes?
How many loops do you need to find?
Okay, the loops should be independent loops. Okay, if you don't have enough equations, try to look for more loops. And I will say that if you draw a loop like this, on the outer peripheral of this network, that is not an independent loop because you can show that that loop is actually the sum of the two individual loops. In other words, if I make a loop like this, say this represents the outermost loop, I can actually let it be the sum of these smaller loops. Okay, I can think of the outer loop is actually the sum of the two smaller loops. So the outermost loop is not an independent loop. You try to find as many independent loops as you can. So this needs some thinking in terms of topology. And if the circuit has very, very complicated topology, that might be difficult for you to find all the independent loops. So the node voltage method is a safer method because you don't have to look for loops. Okay, you just look for nodes, and nodes are easy to find. Loops are not easy to find. Okay, it needs the knowledge of topology. So let's do another example. Example 2.12. This picture here looks somewhat like this, that I have 14 volts over here, and then I have 2 ohms, 4 ohms, 2 ohms, and then I have a controlled voltage source. Okay, 2 ohms, 4 ohms, and 2 ohms here. And that this control voltage source is 3Ix. And then I have them connected in this manner. And then I have a current source over here, 2 amp. Okay, and this value is called Ix, according to what I have in my lecture notes here. Okay, let me see what I need. So I find 3 loops. It's easy to find the 3 loops. Let me call this I1. Let me call this I2. And let me call this I3. Okay? You assign loop current I1, I2, and I3 to the 3 loops you have. And you're pretty sure that the 3 loops are independent of each other because you cannot make one loop from the other one. Okay, so you're pretty safe there. And then apply KVL on each loop. Loop 1, let's apply KVL, then it should be 14 volts equals, okay, you can put it on the right hand side as I did in this thing, or you can take this voltage rise and put it to the left hand side. So I start with 14 volts, should be equal to the first voltage drop, 2I1, okay? And then there's this strange thing over here. Is this a voltage drop or voltage rise? A voltage drop. Okay, so I should give it a positive sign, and then call this voltage drop 3Ix. Okay, as I go around in this loop. Okay? And then I go to loop 2. Loop 2, as I go in this direction, this is the voltage rise. It is either given a negative sign on the right hand side, or you can put it on the left hand side and give it a positive sign. 3Ix must be equal to 4I2 plus Ix. Actually, you can figure out what Ix is. Ix is from these two loops over here. Okay, you can figure out what should Ix be? Yes?
How many ohms is that resistor in the middle?
20 ohms, or 2 ohms, 4 ohms, 2 ohms.
The vertical one.
Oh, the vertical one is 1 ohm, sorry. 1 ohm. 1 ohm. Okay? So, you can actually figure out what Ix should be in this picture. It should be, anybody wants to try what Ix should be? I2 minus I3, right? I2 minus I3, that's Ix, okay? So when you write the second equation down, you have 4I2 plus 1 Ix, okay? But plus 1 times Ix, but Ix is equal to I2 minus I3. But I3 is connected to a current source. So I3 is already known, has to be fixed. Current sources are very stubborn. They cannot allow you to change your values. So I3 must be 2. That's right, negative 2. Okay, very good, negative 2. So then I should have I2 plus 2. Okay? And then together with this equation, the equation that I have over there, which is I2 minus or plus 2, then I have 3 equations and 3 unknowns. Okay, the unknowns are I1, I2, and Ix. 3 equations, 3 unknowns, I can solve for them, and you can do that systematically, I presume. I don't need to go through that. So are there any questions? Because I'm supposed to use this whole lecture to do current loop method, and it seems that I have plenty of time. Okay, before I need to move on to a new topic. What is that?
End of lecture, let's go.
Okay, no, you cannot go. Let's do one more example. So this example is slightly more difficult. So you might get a little bit confused by this example. I really want to figure out how to get rid of this. Because they obstruct my handwriting on the blackboard. But I hope you can read. You can see the trees from the forest. Okay, this is the topology of the example, and I have a 2.6 volts over here, And then I have a 2 amp current source over here, and I have a 1 ohm resistor, 1 ohm over here, 1 ohm over here, 2 ohms, and 1 ohm over here. So everything is 1. So that makes your calculation very simple. You just need to multiply by 1. Okay? So you assign 3 loops. And the smallest loop you can find would be these 3 loops, okay? And then there will be another one over here. So try to assign the loops using small loops. Usually they are independent of the other loops. Okay? And let's call this I2 and this I1 and then this I3. Okay? And there's something special about this topology over here, in the sense that there's a common branch. There's a common branch between these 2 loops. This is called the common branch. Okay? On the common branch, if I were to call that, say, Ix again, like the other diagram over there, okay, Ix should be equal to, if Ix is flowing in this direction, okay, Ix should be equal to what, in terms of I3 and I2, what should I write it as? It should be I3 minus I2, right? Ix is equal to I3 minus I2. But unfortunately, we have a stubborn current source there. Okay, that difference could only be 2. This difference could only be 2 amps because of the current source. That means that I3 and I2 are related. Okay, they are related. When they join in the hip, they cannot be different. Okay, so I3 minus I2 equals 2 amps. Okay, so which means that this loop is sort of made to be dependent on this loop. These two loops are not independent of each other now. Okay, because of that current source. And then now we write KVL for loop 1. Okay, loop 1. If we write the KVL, then we start with the voltage rise. We put it on the left-hand side. It's equal to the voltage drop on the first resistor, which is 1 times I1. Okay, and then the voltage drop on the second resistor. But what is the current that actually goes on this branch?
Wait, don't they share?
What?
Doesn't that first resistor on the top share between the
You're right, you're right. It should be 1 I1 minus I2. That's right. Very good. Thank you for catching that. Okay? Because the current that flows this between this branch or on this branch is actually I1 minus I2. Okay? And that is the first voltage drop. But what about the second 1 ohm resistor? The second 1 ohm resistor would have I1 minus I3, right? I1 minus I3. So this is this one over here. If I draw it out, it's I1 minus I3. That is the current that's going there. And then the last voltage drop. What is that current that goes through the last voltage drop? It's just I1, right? Plus 1 times I1. So I have one equation. Okay, one equation from loop 1. And now I look at loop 2. Okay, loop 2. There's no sources over there. Okay, if I walk around, I would have if I walk around in this loop, okay, I will have one. Let's look at the voltage drop on this. The voltage drop on this is just 1 times I2. Okay? Plus Vx. And we don't know what this voltage drop is at this point. Let's assume that across this current source, we have a voltage drop in this manner of Vx across that current source. Okay? If we walk around in this loop, then there's a voltage drop of Vx in this direction, and then I have to add this voltage drop, okay, which is now actually a voltage rise, so it should have a minus sign of I1 minus I2. Okay, that is the kickoff voltage law that you get by walking around in loop 2. Okay? Then you now walk around on loop 3 and try to write another kickoff voltage law. And as I walk around in loop 3, I can start with this voltage rise going from here to here. Okay, and put that on the left-hand side. Vx must be equal to, this would be a voltage drop going from here to here. And what is the current that goes through here? It's I3, right? So it's 2I3. 2I3. Okay, and then you have this other one, the last one, which is 1 ohm times, what is the current that goes through that one? Let's assume that the current is going in this direction. It was said to be I1 minus I3, but if we consider this to be a voltage drop, then it should be I3 minus I1. Okay, that is the last loop that we should have. So how many equations, how many unknowns do we have now? We have I1, I2, I3.
Vx.
And then we have Vx. Right? And we have this equation that marries them. Okay, so we have 1, 2, 3, 4 equations and 4 unknowns. Okay, there should be enough equations to solve for the number of unknowns you have in this problem. Okay, is that clear? Or you want me to go into some detail in solving these 4 equations? Not necessary, right? All of you are professional at doing that. I'm sure that you can know. You want to plug this equation into that one, eliminate some unknowns, and find I1, I2, and I3. Okay? So, any questions so far on the loop current method? Yes?
On the first equation, you treated that 1 ohm resistor that's vertical right in the middle. You treated that as if it was a voltage drop in one direction, and then in your third equation, you treat it as a voltage rod.
Right.
Or
Right. I treat it as a voltage. That's a very good question. I treat it as a voltage drop when I was doing this loop, because I was imagining a current flowing in this direction. Okay. If the current is flowing in this direction, there should be a voltage drop. And then I asked myself, what is the current that flows in this direction? It's I1 minus I3.
yeah.
Okay. Then I put that as the resistance times the current.
Yeah.
That should be equal to voltage drop. But as I go in the opposite direction, I have to change my mindset a little bit. Okay. I can either think of this as a voltage rise,
Yeah.
okay, as I see from this diagram, or I can think of a current flowing in this direction, giving rise to a voltage drop, okay, and give it a positive sign. So if I ask myself, what is the current that's flowing upward? The current that's flowing upward is I3 minus I1, the negative of this one.
Yeah.
And then I can still imagine it to be a voltage drop and put a positive sign in front. It's I is the resistance times the current. Okay? So it doesn't matter as long as you keep your convention correct. You always get the right answer. Okay, if you think of it as a voltage drop in this direction, you make sure that the current you put in is in this direction. If you think of it as a voltage drop in that direction, you better make sure that the current you put in there is flowing outward.
Yeah.
The two currents are just opposite inside of each other. Okay? Any other questions? So seems very simple, right? Very simple to do, and I'm sure that you enjoy doing your homework. So let's talk about the concept of a super loop. Super loop. There is a super loop in this example over here, and it's been discussed in the textbook, and let's think about what it is. Okay? And a super loop is usually forced or given by the presence of a current source. Okay, if I want to define what the current source is, it is something that looks like this. And the current that flows through it is fixed. Okay, you can have only IS coming into it and IS going out of it. So it's a very stubborn source, but it is flexible in the other direction. It can have any amount of voltage drop across it. So any amount of voltage drop. Okay, so if I think of it as having a, say, voltage drop V across this current source, and that voltage drop is not controlled by this current source. The current source has no control of it. It's controlled by how it is tied to the external wall. And that V can be anything depending on what it is tied to. If you tie to a very big resistor, in the outside wall you have a huge voltage drop. If you tie to a short circuit, it has a voltage of 0. If you tie to a negative resistor, it will have a voltage that is negative. Okay, you probably haven't heard about negative resistors yet. Okay, you will learn about negative resistors in a little while, maybe in chapter 3. Okay? Does anybody know what a negative resistor is?
It's imaginary capacitors and inductors.
Not really. Not really. So if you have this law, P equals VI, and then you have V equals IR, right? So P equals I squared R. So if R is negative, what happens to P? P is negative. So it's a kind of resistor that gives you power instead of absorbing power from you. So you like it, right? It's a source of energy instead of a sink of energy. Okay? So you have a lot of this kind of electronic circuits that can do this kind of wonders for you. Give you energy instead of taking energy away from you. But you have to supply some other sources of energy in order for it to behave like that. Just like something that gives you energy is like your amplifier in your cell phone. Something comes in with very small energy, and by the time it reaches your ear, it's very loud. So something must have happened in there by amplification. So small amount of energy is converted to a large amount of energy. And it can be done by a negative resistor, or an amplifier, or a transistor. You'll learn more about this later on. Okay, it gives out power. But you have to take power from somewhere else. In the case of a cell phone, it's from your battery. It receives a very weak signal from somewhere far away from Chicago, say, some far away places, but then it makes the signal grow bigger. Okay? We'll talk more about this later on. But this is a current source. Its voltage across it is quite flexible, but its current that passes through it is not flexible at all. So in that sense, it resembles an open circuit. So it resembles open circuit. Okay, so it is almost like that circuit over there, except that a fixed amount of current can jump across this gap. This open circuit can take any amount of voltage drop across it. Okay, but the current that passes through it is 0. Okay, that's what a open circuit is. So think of a current source as an open circuit with currents jumping across it. Okay, the current jumping from one end to the other one. So you should think of this current source as being an open circuit. Because it's an open circuit, and that a fixed amount of currents jump across it, these two current loops are actually connected to each other. They are not independent of each other now. You should think of this loop as being married to each other, joined in the tip, and there should be a global loop that looks something like this. Current cannot pass through it because nobody can change this guy. Okay? So the current would choose to flow like this. So if there's any current that flows, it flows in this loop, in this manner. It avoids this current source. Because the current source behaves like an open circuit. Yes?
So instead of doing loop 2 and loop 3, could we have just done one big loop?
You could have done one big loop. Okay, you could have done one big loop if you want to. You could have written KVL for this one big loop. Okay? And in fact, if you substitute this equation into that equation, okay, and write the KVL for the large loop, you get that equation immediately, which is a combination of these two equations. That is a super loop method. Okay, you write the equation for one big loop, and then you get the consolidation of these two equations. Okay, because this actually is an open circuit, to be honest, right? It behaves like an open circuit. So there's actually no loop going through it. There's actually no loop going through it because it behaves like an open circuit. So let me see. So for instance, I can choose to write the third equation in this manner. I can choose to write equation 3 in this manner that looks something like Vx equals to 2 times I2 plus 2 plus 1. And this is I2 plus 2 because I'm making use of this equation. Okay, I'm not trying to think of I3 as being independent of I2. Okay, I3 and I2 are related to each other by this equation. So whenever I see I3, I use this equation to replace it. So the first term on the right hand side just becomes this one. And then I have I3 again. I'm going to do this replacement. So it will be I2 plus 2 minus 1. So I can write the equation 3 in this manner. Okay? And now if I plug equation 3 into equation 2, and again write I3 in terms of I2, then I have two equations and two unknowns. And I can easily solve for them. Can you see that? We plug that equation into the second equation and make sure that whenever I see I3, I replace with I2. I have two equations, two unknowns, and you can say that those equations come from a super loop and this small loop over here. Okay, two equations and two unknowns. That's another way of looking at this problem. Are there any questions? Or you want me to plug it into equation 2 and then rewrite equation 1 again for you? No need, right? All of you are geniuses. You can see that this I3 can be related, and then this one will just go away. Okay? I don't need to do that. Okay? So, then I'd like to revisit the concept of a supernode. What is a supernode? A supernode is caused by the presence of a voltage source. Okay, just like a superloop is caused by the presence of a current source. So I'd like to redefine what the voltage source is. A voltage source is given by maybe a symbol, something like this. Okay, with a source and then something that looks something like this. Let me put the current in this direction. Okay. It has the stubborn property that Vs cannot be changed. Okay, but you can have any amount of current that passes through this device. Okay, so it's the second line here that is different. So any amount of current through it. Okay? So in a sense, it resembles a short circuit. A short circuit is like that. You can pass any amount of current through a short circuit. Okay, it resembles a short circuit, but with a voltage drop across the short circuit. Okay, so it behaves almost like a short circuit, but there's always a voltage drop across it. Okay, so this is almost like a short circuit, but there's always a voltage drop when you go from here to here. Okay, not exactly like a short circuit, but behaves like a short circuit because it can pass any amount of current through it. So let's look at the supernode concept again. In the node voltage method. And we have this example that we can go through again. I think this example confused a lot of you, so maybe it's worthwhile going through that again.